Hey gang, Buckley here. We're going to do two problems related to friction. This should be some help with your current homework assignment. So let's take a look at this one. We got a guy on a ladder. He didn't set his ladder up right. Always important to set your ladder up properly before you climb. He's 180 pounds, assuming his center of gravity at G, okay? And he's got a 3-foot ladder away from the wall before he felt the ladder slipping. The ladder's at 60 degrees, it's lightweight, and the contact at B is smooth, so no pad there at B. So we've got friction contact down here at A. This is 60 degrees. Here at G, we've got 180 pounds. We're going to assume that the ladder is fairly lightweight. So that's going to be the center of gravity for the whole system. Okay, and we're being asked, what's the coefficient of static friction between the ground and the foot pad at A if he is basically on the verge of slipping, right? So the ladder just felt like it starts slipping. Okay, so let's work through this problem. So we are given a couple things. Given the diagram, the combined center of gravity at G with weight equal to 180 pounds. B is smooth, and friction at A. And we're going to neglect the weight of the ladder, okay? So I'm being asked to find this coefficient of static friction at point A. Okay, so let me go ahead and draw a rigid body of this situation. I'll go ahead and draw that here. So I'm going to start with my free body diagram. So there we are. Down here at the ground, I've got NA, the normal, and I've also had a frictional force. So if this is going to push back, my frictional force is actually going to go in that direction there. So I'll call this Fs. And that's going to be equal to mu s times NA at the point of slipping. I've got my center of gravity here, 180 pounds. Make that a little clearer for you, 180. Okay, and then up here at B, I just have a horizontal force. We'll call that Bx. Okay, so B is smooth, right? So I'm just going to get that Bx. All right, so now I can just do based on this free body diagram, I can do a sum of the moments about A is equal to 0. That's going to allow me to solve for Bx. So when I do that, I get negative Bx. This guy is 60 degrees, right? So Bx times 10 cosine 60 degrees plus 180. It's going to give me a positive moment, that weight, 180 times 10 cosine 60 degrees minus, this is basically going to be at 3 feet from the wall, right? Okay, so 10 cosine 60 minus 3 should put me right at that center. Okay, if I solve this, I get Bx is equal to 41.57 pounds. Now that I've solved for Bx, right, I'll also look for some of the moments or some of the forces in the y direction is equal to 0. I get negative 180 plus NA. So NA is 180 pounds. Sum of the force in x is equal to 0. I'm going to make use of this Bx that I found. So I've got 41.57 minus Fs, which is mu s times the normal, and the normal I solve for being 180. So I can go ahead and back solve this, and I get mu s is equal to 0.231 for the coefficient of static friction at the verge of this starting to slip. Okay, cool. That one was fairly straightforward. Let's look at one that's a little bit trickier. Okay, so we've got a situation here. Beam AB has negligible mass and thickness and supports 200 kilogram, 1,961 Newton weight, 1961 newtons. It's a uniform block, so I know its location is going to be dead smack in the center there. It's pinned at A, okay, and rests on the top of a post. That would be this post BC, which has a mass of 20 kilograms. So there's my mass there, 196 newtons, and negligible thickness. P is 300 newtons. Okay, so we'll make a couple annotations there. Determine the two coefficients of static friction at B and C if the post slips simultaneously in B and C. Okay, so we got this post that's sitting under this plank. The plank itself is pinned at one end and it's supporting a uniform mass. We're going to pull this post out with a force of 300 newtons as directed. So what we're being asked is basically these 2 points are going to slip simultaneously. So in order for them to slip simultaneously, what should those coefficients of friction be? All right, cool. So let's state our givens. Given diagram, I've got my two weights. W1 is 1961 newtons. W2 is 196 newtons. P is 300 newtons. Being asked for mu S. I'll call this mu SB and mu SC if simultaneous slip. Okay, so let me start with an RBE of, I'll do the top member first, AB. So if I pull this together, I'm going to have AY. Well, actually, let me think about this for a sec. So if I'm pulling this out, the force of friction on this side is going to go like this, and on this side is going to go like that. So I'll actually have a force of friction here, FSB. FSB. And a normal, NB. FSB is mu SB times the normal. And one important thing here, right, so it said negligible thickness, negligible mass and negligible thickness, okay, which means that this point is going to wind up acting down through the middle, right? So the fact that these are also, both of these are negligible thickness means that this force of friction is basically going to pass through this point. All right, so over here I got AX and AY for a pin. Here I've got a normal and a force of friction. I was a little strategic about how I drew this, right? But I'm basically thinking about the action-reaction pair that must be happening here along this surface. Then I've got a weight acting down in the middle. So this is 1961 newtons, and that's acting obviously halfway. Okay, so I'll just put that on there. 1.5 meters. All right, so I'm going to go ahead and solve this. I'll do some of the moments about point A is equal to 0. And I will then solve for what I need for the normal force here. So I get negative 1961 times 1.5 plus NB times 3. NB is equal to 980 newtons. Okay, and that's about as far as I can go there. So I solve for the normal. This force is going to be the unknown coefficient of friction times that normal. So now let me switch over to the RBE of member BC. Now, member BC has a weight down in the middle, not forget that, 196 newtons. It's got a normal down at C. It has a normal on this side too, which we just solved for. NB is 980 newtons. It is going to be pulled in this direction. Let's see, that is going to be 1.75, so this would be a little bit 300 newtons at 435. Okay, now I have to deal with the forces of friction. So on this surface here, since I'm pulling in this direction, I would have a frictional force here, FSB is equal to mu SB times 980. Down here, I'd have the similar FSC is equal to mu SC times NC. So this is very important, right? So we were given that there's simultaneous slip at B and C, so we can use these expressions, we can use Coulomb's law at that one point. If we were not told that those were simultaneously slipping, we could not make that assumption, right? Okay, so I've got a complete free body diagram now. Let me count knowns and unknowns. So I've got 1, 2, 3 unknowns, mu SB, mu SC, and this normal down at the bottom. Okay, so let me go ahead and I'll do a sum of the moments about C is equal to 0. And that'll allow me to actually solve for this mu SB. So let me go ahead and do that. So I get, let's see, negative 4/5 300 times 0.75. The weight's going to pass through. 980 is going to pass through, so I'm just left with this guy, plus mu SB 980 times 1.75. If I solve this, I get mu SB is equal to 0.105. Cool. All right, now I can do sum of the forces in Y is equal to 0. I get negative 980 minus 196 plus 300 times 3/5 plus NC. NC is equal to 996 newtons. Now I can do sum of the forces in X. Some force in X is equal to 0. I get 4/5 times 300 minus mu SB times 980. USB I know now is 0.105 minus mu SC times NC. NC is 996, so I can go ahead and solve for mu SC. When I do that, I get mu SC is 0.138. Okay, so a little bit more complicated. I had to solve essentially a machine problem first before I could delve in and deal with the frictional forces. Well, actually, I used the frictional forces in combination with this, this machine problem, okay? All right, guys, that's what I have for you. Hopefully that's helpful on your current homework.